about PDF determination through machine learning.
Okay, thanks. Thank you for inviting me. So I'm sure that most people in the audience would have thought that PDF in my title means probability density, but that's not what it actually means, and therefore I have to start by explaining what it does mean. I will be talking about objects, PDFs, which are Parton distribution functions that are in some sense probability densities or other generalized probabilities. And more specifically, I will be talking about probabilities of probabilities. So I suppose that the pun in the title is appropriate. And so I start by explaining what the problem I'm addressing is and how this has been addressed by myself with a bunch of other people called an NPDF collaboration over the last 15 or 20 years. And then I'll spend I'm sorry. Yes. Yeah, the camera is on the other side. Sorry, I hadn't realized. You're right. Yeah. I'm used to these cameras that follow the speaker, but I hadn't. I was looking at the audience rather than at the camera. Very good. Okay, so I'll be spending the last part of my talking reviewing work that we've been doing over the last 3-4 years, and that falls under the generic heading of machine learning. So as I said, by PDF, I mean Parton distribution functions. Parton distribution functions are objects that encode the structure of the proton or the nucleon or hadrons in general. Now, the current theory of strong interactions has this wonderful property that we call factorization that says that if you want to describe a collision between two protons, as say at the Large Hadron Collider of CERN, this can be done by factoring the calculation into two parts. A part which is described by the PDFs, the Parton distribution, which tells you the likelihood in a non-technical sense of extracting a constituent of the proton, so let's say a quark from the proton itself, which is then folded with some calculation which can be done in perturbation theory by calculating Feynman diagrams, where you have the fundamental degrees of freedom of QCD in the initial state, so say quarks, anti-quarks, and gluon, and whatever final state you want to produce. So if you want to calculate, say, the Higgs production cross-section at the LHC, the way you do it is you calculate a bunch of Feynman diagrams with initial state quarks and gluons and Higgs in the final state, and then you fold this with Parton distributions. So, anything that you compute at a collider like the LHC, where you got protons in the initial state, requires the knowledge of Parton distributions. And matter of fact, this knowledge is the dominant source of uncertainty in most cases. For example, this is a breakdown of various uncertainties on the Higgs cross-section taken from the official CERN website, and you see that this delta PDF plus alpha S is the bulk of the uncertainty, or at least it was 2 or 3 years ago. Now, as I mentioned, the part of this calculation that involves quarks and gluons in the initial state can be done using perturbation theory, so calculating Feynman diagrams, but the Parton distributions, the PDFs themselves, cannot be calculated, or rather, they could be calculated from first principles if we were able to solve QCD in the non-perturbative regime, but we can't, so well, maybe they could be estimated on the lattice, but mostly they're actually extracted from experiments. So the way this is done is you calculate the cross-section or any observable for any generic physical process at some facility where you have protons in the initial state. This is obtained by folding what you calculate in perturbation theory with PDFs. You compare the results to what you measure, and you solve the inverse problem, and you infer the PDFs from the comparison of the calculation where the PDFs are an unknown to what you actually measure. And this is currently done by using about 5,000 experimental data points, which come not only from recent LHC proton-proton collisions, collisions, but from older tevatron proton-antiproton collisions, and from experiments where actually one was doing electron-proton, muon-proton, neutrino-proton, I mean, and all kind of collisions in which you have at least one proton in the initial state. At the end of the procedure, you end up with something that looks like this. These are the PDFs. So let's say this red one is the up valence, so-called distribution, which means the difference between up minus anti-up quarks. So that's something that, say, peaks at the third, because so this which you have on the x-axis is the fraction of the proton mass or momentum that is carried by the corresponding parton. So this guy peaks at a third, roughly speaking, because there are 3 quarks in a proton, and the up quark is twice as big as the down quark because there are 2 ups and 1 down, very, very crudely speaking. And then you have anti-quarks and gluons and so on, and this is at a particular scale, i.e. at a particular resolution. Now, as you can see, these are curves with uncertainties, because you're extracting them from data that have uncertainties, and also you are dealing with a problem that, strictly speaking, mathematically is ill-posed, because you're extracting quantities which are functions. So, you know, they are, roughly speaking, probability densities. I say roughly speaking because they need not be positive semi-definite. They could be negative, so they're not quite probabilities, but you can think of them as kind of probabilities. And moreover, you're extracting these things with an uncertainty, so you're really extracting a probability density of probability densities. So that's a functional, if you wish. It's a function of a bunch of functions, and you're doing this by starting with 5,000 data points, which may seem a lot, but it's still much less than the infinity of infinities of functional. So at present, these uncertainties are known quite well, and you can get a feeling here for the level of knowledge of PDFs. So what I'm plotting here are what are called parton luminosities, which means the combinations of 2 different incoming partons that produce a given final process. So for example, if you're looking at Higgs production at the first order in perturbation theory is produced by having 2 gluons in initial state. So you want to look at the gluon-gluon luminosity, which is shown here. And what is being plotted here is a heat map in the plane of the mass of the final state. So if you're doing, say, Higgs production, the mass of the Higgs is about 100 GeV. So you want to look along this axis. And Y here is the boost along the direction of the collision. So Y equals 0 means that the Higgs is produced centrally, while Y equal +1 that is produced going to the right, and so on. It's a Lorentz boost, the log of the ratio between the Z component of the momentum and the energy. Okay, so a centrally produced Higgs, 100 GeV, you look here, yellow, 1%. So, you know the Pdf uncertainty to 1%. You may notice that this is rather lower than what I had in the previous slide, but the previous slide was 2019. This is 2021. So you can also get a feeling for the sort of progress that we have. And I should stress that, I mean, here I'm showing the uncertainty, but we really need to know the full correlation matrix. So we have this infinite dimensional covariance matrix between uncertainties. I can tell you not only what the uncertainty on the gluon at a certain x is, but also what the correlation between the uncertainty of the gluon at that x and the uncertainty on the, I don't know, up quark at a different x is. And as I just mentioned, this is recent and it's very accurate, and you can get a feeling for the improvement in accuracy by looking at these contours. This is the Higgs cross-section and the Z cross-section, the Z boson. These ellipses show purely the Pdf uncertainty. So it's just the uncertainty due to the PDFs. And the 1% thing that I was showing in the previous slide is this small circle here. The bigger ellipse here is our own determination from 5 years ago. This one is called an NPDF 4.0. The previous one is an NPDF 3.1, which is consistent, but it has a much larger uncertainty. And then you see other groups that are doing this thing with much larger uncertainties. And this instead is the Z and W cross-section. So you get a feeling both for the progress, I mean, 5 years ago versus now, and for the difference between determinations performed by us using AI or machine learning tools and everyone else who uses more conventional approaches, as I'm going to discuss. And you'll notice that our uncertainties are smaller. Now, our uncertainties are smaller where there are data to constrain the result. But if you instead look at regions where there are no data to constrain our result, typically our uncertainties are bigger. So what I'm showing here is, well, it's kind of technical. I don't want to enter into the details, but this is an angular distribution. You can think of this as an angular distribution for the production of a gauge boson. And I'm now looking at the angular distribution for the production of a gauge boson, where the gauge boson is a hypothetical heavy partner of the Z with a much larger mass of 5 TeV as opposed to the 100 GeV of the known Z. So, it's a hypothetical beyond the standard model particle. And the blue band here is what we get, while this is what everybody else gets. You see that the uncertainty is bigger, and also other people have a prediction for a precise signal, which is an asymmetry between the forward direction and the backward direction, which we don't see at all, which is what you'd expect if you have no information. So, our results are characterized by the fact that we have smaller uncertainties where there are data and bigger uncertainties where there are no data. So this brings me to the problem of Pdf uncertainties. Now, problem of Pdf uncertainties is a serious issue, and people realized that in the early 2000s when the LHC was coming up, because, of course, people realized that if they wanted to discover the Higgs or supersymmetry or God knows what, then they'd better be able to calculate what happens. And in order to calculate, you needed to know these pattern distributions. So there was this workshop that I was involved in that ran for several years called the Hera LHC workshop. LHC was in the future then, and Hera was the previous collider that was an electron-proton collider at DAISY in Germany, which was the main source of information on pattern distributions. And I'm taking this plot and this sentence from the proceedings that were produced at the end of the workshop. There was, well, 2 big volumes where we, or rather people who were then doing pattern distributions, we were not yet, benchmarked the results of various groups, and the conclusion was that the patterns extracted using a very limited data set are completely incompatible, even allowing for the uncertainties with those obtained from a global fit with an identical treatment of errors. The comparison illustrates the problem indeterminate. In other words, what people did was, let's say everybody uses a small subset of the available data, the same subset, then everybody produced a final result, and the results disagreed completely with each other, and moreover, they disagreed with the result that everyone had when they used the full data set, which was different for everybody, rather than this restricted data set. So there clearly was an issue. Now, the issue, the origin of the issue can be understood by looking at what people did. I mean, what people did was basically to assume some parameterization of the PDFs. They assumed some, I mean, I've shown these distributions as a function of X. So what people did was try and guess a possible functional form and say a typical functional form in the early 2000s was like this. This is the gluon PDF, but all the quarks and so on, each of them has its own functional form. A slightly later one from 2005 started looking like this, and one from 2018 from a group that still uses this approach looks like this. So, a bunch of parameters where you add more and more parameters and you fit them to the data. Now, of course, yes. Yeah, that's a good question. So please, as a general comment, I'm trying to keep the level, not non-technical, because I realize that there are people in the audience who are not from high energy physics. But if there is either something you'd like to know in more detail or something which is very obscure, please stop me. Yeah, so good question. So this form, historically, the very first PDFs used as a parameterization simply x to some power times 1 minus x to some other power. Now, the 1 minus is due to the fact that x equal 1 is the kinematic threshold. That means x greater than 1 would mean you got a parton that carries more than 100% of the fraction of the hadron. So PDFs must go to 0 at 1. The idea that they go to 0 as a power of 1 minus x is motivated by a bunch of semi-quantitative counting rules, as they were called, which were based on assuming that you could calculate these quantities from simple leading order Feynman diagrams, which you cannot. But but you know, just to get a sort of feeling of what you'd had. The small x instead, x, oh, I'm sorry. The small x, x to the a, is due to the fact that it turns out that 1 over x is like the energy of the center of mass collision of the partonic process. So small x means high energy, and the high energy behavior is supposed to be dictated by non-perturbative QCD, and in particular by Regge theory, which is something that was developed in the 50s and 60s based on unitarity. And then Regge theory predicts that you should have a power-like behavior in 1 over s, and that leads to the, so the original idea was x to the 1 times 1 minus x to the, sorry, x to the alpha 1 minus x to the beta, but then people realized that that didn't quite work, so they simply started adding parameters. And you know, the simplest thing was to add a polynomial, but then they started actually adding fractional powers, then they started adding square roots, and then they started having multiple, you see, 1 minus x to some power, 1 minus x, yeah, 1 minus the square root of x, sorry, to some other power, and so on. And you know, it started being so the original motivation was kind of based on intuition, and then it just became a game of fitting. But then you see what the problem is, that the result depends very much on what you assume. And indeed, these are quite recent results from a PDF set from a few years ago from a group that is using this very big parameterization. And what's being compared here is their old previous determination to the new one. And the bottom line is that by adding new data, uncertainties, instead of going down, go up, basically because they realized that their previous parameterization was not general enough, so they had to add a bunch of parameters, and then, of course, uncertainties go up. But that means that the previous parameterization was completely biased because, you know, it was overly restrictive. So this is a problem, and this problem is not, maybe there was a question? Yes.
But I'm trying to figure out what is the state of art of lattice QCD simulations. What is the?
Oh, the lattice QCD simulation. So the lattice QCD simulations typically determine moments of the PDF. So the integral over all x of one PDF. And at present, lattice simulations are starting to get a couple moments of the PDFs. So sorry. Right. So what the lattice simulation tells you is integral dx x to the a of f of x, where x is the PDF, and this is called FA, the 8th moment of the PDF. So what lattice simulations give you currently is F2, F3. The moments of PDFs are, so if you ask why, that's because you can prove using the Wilson expansion that moments of the PDFs are matrix elements of local operators in the proton. So for example, the second moment, so F2 would be the matrix element. So F2, let's say for the up quark, would be the matrix element in the proton of the up quark contribution to the energy momentum tensor. So that would be, say, up bar, well, d mu gamma nu plus sim u p, and of course this has some tensor structure, so you must extract the tensor structure. What you're really getting here is, well, actually, I guess what I mean is that this is equal to f2 times some tensor structure like g mu nu minus. Okay, and so what the lattice gives you is a couple of these for a couple quarks and antiquarks. So at present, with big uncertainties, in the future, near future, maybe in the next 2-3 years, it will be possible to actually use this information as a further input to a PDF determination on top of the data. But at present, it's not yet, I would say.
Plus, there is the problem that they are even ill-defined because of lattice is Euclidean and everything else.
Because of
lattice is Euclidean, and then you have yeah, fine.
There, okay, of course there are further, I mean, relating these matrix elements to, so you know, this would be the subject of a separate talk, I guess. So as a baseline, first of all, in the lattice, typically you measure these quantities in the Euclidean, so you have to do an analytic continuation. Also, you have finite size effects. Also, what you determine in, or what you use in the calculation I'm talking about are PDFs determined in the MS bar typically MS bar factorization, while in the lattice you have a different renormalization scheme, so you must relate the two. Now, recently there have been suggestions that you can actually calculate moments, that you can bypass this relation between Euclidean and Minkowski through some trick, which is, however, an object of a wide debate in the lattice community. So it's, yeah. X is an integral from 0 to 1, because you can think of X as the momentum fraction, as a fraction of the proton momentum, which is carried by. So I guess what I mean here when I write F2, I really mean the ratio of this thing between the total matrix element of the, say in this case, energy momentum tensor in the proton itself.
Your motivation for describing this is that you're saying, well, this isn't moment. You could do moment matching with this approach versus this kind of parametric guessing stuff up here. So this is, you're describing it as this is a better approach than what?
No, he asked me whether these quantities could be computed on the lattice, and the answer to the question. So whether the quantities I'm talking about are these f of x, which I'm interested in because they are the things that I use in order to calculate cross sections at the LHC. Okay.
It seems better to do a moment matching strategy like this than this thing here, right?
Okay, so the moments can be in principle calculated numerically on the lattice. Of course, when you calculate a cross section, so for example, when you do a comparison between data and theory for an LHC process, you can do that either in the original space or in moment space. And matter of fact, much of it is in practice done in moment space, but that's a separate issue. That's a computational issue where indeed, like you say, it may be convenient to do moment matching. Even though at the end of the day, what you're interested in is the function f of x, because that's what you're supposed to integrate.
But there are constraints on it.
There are constraints on it, as I was saying. As soon as these constraints will start being numerically relevant, we will start including them. Trouble is that at present, from the lattice, only a couple moments are known, and then with huge uncertainties. So the constraint that would be imposed by adding this couple numbers to our determination on top of the 5,000 data points at present are not that interesting, but it's of course true that once these are known reasonably well, they impose an orthogonal constraint, because then you know the integral rather than just knowing a couple points on the function, and then of course, yeah.
Maybe one day, but not yet.
That's right.
That's something that has already been done in practice.
Yeah, of course.
It's not included by default, but there is someone that.
Yeah, of course we try. I mean, the statement they don't have a big impact is based on actually doing it, not on estimating what might happen. I mean, and at present, you know, we can put them in and nothing happens basically.
Sorry, and then apart from lattice calculation that we may do in the future, are there robust theoretical constraints on the functional form of the PDF?
Not really. I mean,
so you don't impose
there are,
anything.
well, I mean, there are, so first of all, there are constraints related to some rules. I mean, the fact, for example, that because the second moment for each PDF is a contribution to the momentum, the sum of the second moments must add up to 1, for example. So this is a kind of constraint, which is not a constraint on the functional form, but it's a constraint on the sum of the integrals. There are some integrability constraints. For example, you know that at small x, the power that you got the power that you got here is such that some moments must exist. For example, the second moment must exist, and that obviously limits the highest degree of divergence at small x that you have. So you have that kind of constraint. There are positivity constraints in the sense that PDFs are not positive semi-definite, as I mentioned, but that's a statement that depends on the factorization scheme. So in some factorization schemes, then you can show that they are positive semi-definite, and then you have that kind of constraint. But there is no constraint on the functional form, like saying we must have x to some power or something.
Right, but I was so. And then, do you impose all these constraints in your way?
so so I
Then
didn't
a
get to
GDF.
what we do,
Yes,
but
yes, maybe you
I'll
can-
soon get there. But of course, what we do includes all constraints that are motivated, that are based on the underlying quantum field theory. So typically, what we do is we impose the sum rules, and then we check what would happen if we relax them, and check, for example, that the sum rules would come out automatically from the data. So the data like the sum rules to be satisfied, but because we know that they are a strict constraint, then it's advantageous to impose them, because then you have an extra constraint, though we also not impose them in order to check that everything is consistent and we are not pushing the determination in some direction.
Yeah, just a clarification. So you mean that all the PDFs for all particles that you're considering have to kind of sum to something so that they kind of make up the total momentum? Is that such a
Yeah,
Thanks as
so
well.
there is a set of sum rules. So, for example, well, there is a momentum sum rule which says that the second moment, so that says that the sum over I of Fi2 must be equal to 1. Okay, so that's one constraint. And then you have another constraint which says that the total number of, first moments are actually matrix elements of vector currents. So the first moment tells you the baryon number that is carried by the quarks, and then you have a sum rule that says that let's say that F1 up minus F1 anti-up must be equal to 2, and that F1 down minus F1 anti-down must be equal to 1, which is like two up quarks and one down quark, except that they are net numbers of quarks minus anti-quarks. So again, you have this constraint, and I guess that's probably it, actually. Well, of course, yeah. And then of course, F1 strange minus F1 anti-strange equals 0, because the proton does not carry strangeness, and likewise for heavier quarks. Okay, so you have these constraints. Okay, right. So you see what the problem of fitting a parameterization is. And this problem is highlighted by something that happened in the mid-90s when at the Tevatron, they thought they had discovered quark compositeness. And that's because they were looking at the cross-section for producing high PT jets. So, jets of particles with large transfer momentum. They found a huge excess in the data in comparison to the theory prediction. But then they realized that that was simply due to the fact that the underlying gluon Pdf was not known well enough, and as soon as they redetermined the gluon Pdf, the effect went away completely. Now, this highlights the fact that there are two problems of increasing seriousness. One is that you're extracting functions from discrete points, so you have a problem of interpolation. But the other is that the data only constrain the PDFs in a limited X range. So when you go at very small X or very large X, PDFs are not constrained by the data. So you have a problem of extrapolation. And indeed, what was being probed here was the gluon in a region which would correspond to a very heavy final state, at least for the time, like the Z prime I was talking about previously, where PDFs are unconstrained, and so this would be large X extrapolation, and this is a problem that has resurfaced time and again. For example, in the mid-90s, when people turned on the Hera collider, they started measuring PDFs or structure functions at small x, so that was higher energy, and they discovered that the behavior was very different from what they expected, and this is illustrated in this plot, which was produced in the early 2000s, where you see that the behavior of the gluon pre-Hera was like this, and post-Hera was like this, and this is, again, a reflection of the fact that people had some prejudice. They picked some functional form with some range of the exponent, and then they realized that it didn't quite work. So, this does not look good, and this is where we come in. So in the early, I'm sorry, this slide is completely unreadable. It wasn't unreadable on my screen. I'll try to improve it. Anyway, this is supposed to be a timeline where here you should be able to read that in 2002, myself and a group of collaborators, in particular, Jose Latorre, had the idea of using neural nets as a way of parameterizing PDFs, and that was then a proof of concept. And then, it took some time. In 2007, we produced the first PDF determination. And currently, if you follow, if you were able to read the timeline here, which you're not, you would discover that now the PDFs that we produced are the most widely cited. So, in the end, the proposal has turned out to be successful. So, yeah. Yes. Well, my friend Jose Latorre was using neural nets for all kind of weird applications. He was consulting. Well, he's a high energy physicist, but he has many interests. Right now, he's the director of the Center for Quantum Computing of Singapore, and also the director of the Abu Dhabi Quantum Computer. At the time, he was consulting for a company that was producing croissants in Barcelona, and they had the problem that the way they used to predict the demand of croissant for the next day was based on what happened the previous day. So if there were leftovers the previous day, they reduced production, and if they sold out, they increased production, which was not very efficient. So he had the idea of telling them, well, I can try and fit a neural net to your last several months and see whether I can predict trends. And so, I was talking to him at a center of which that he was trying to establish, and I think now exists, and I think he's now the director in Benasque in Spain, in the Pyrenees. And he said, at the time we were working on exact renormalization groups, so something totally different. And then I told him about this business with the PDFs, and he said, well, neural nets can do various things. Why don't we try to do better than these stupid functional forms? And you're absolutely right that many people at the time said, well, it doesn't look so good. So we had to produce a first determination, and then it took a while to make it work. So I guess it's partly serendipitous or accidental.
The first neural network was a piece of uncrafted Fortran code.
Yes, yeah, absolutely. Yes, yeah. Okay, right. So what's the general idea? So the problem is how to determine a probability distribution of probability distributions from a discrete set of data. So there are really two problems. One is what to use as basic interpolators instead of the functional forms, and the other is how do you get the probability distribution. So starting from the end, the way we get the probability distribution is by using a Monte Carlo approach. So we start from data. Let's say we have these 5,000 data points. The 5,000 data points are really 5,000 by 5,000 covariance matrix, because experimentalists give us uncertainties and correlations, and so all these things are correlated. Not everything is correlated. It's block diagonal, if you wish. Not everything is correlated. So for example, an LHC experiment is not correlated to a hair experiment of 20 years ago, but so that block is zero. But by and large, everything is correlated. So what we do is we turn these 5,000 data points into a Monte Carlo representation, meaning that we produce pseudo data such that if you take, say, the average over the set of pseudo data replicas, that's equal to the central value that the experimentalists give us, at least in the limit of infinite number of replicas, and the covariance is the correlation, and so on. There's a question?
Yeah, the question was the data is, I guess, some kind of integrals over the PDFs times some kind of functions, which are the cross sections.
Yeah. So that right. So the what's the relation? So let me get back to.
I guess that was like the first slide.
That was in the very beginning. Yeah. Okay, so this was very schematically written in one of my first slides, if I can get there. Unfortunately, these plots are too heavy and it takes forever. Yeah, all right, 2, 3. Okay. So this is schematically written in this equation up here. So say sigma is a cross-section that you measure. F are the PDFs. These guys are all functions of X. And this sigma hat is a cross-section, or something that you calculate from Feynman diagrams that will depend on the kinematics of the final state. So say you're a Higgs boson with a certain PT and boost and whatever. And then it will be integrated over the X variables on which the PDFs depend. So these convolutions, as they are written here, are integrals over x. So integral over x1 and x2 that must be performed in such a way that the final state kinematics is related to the momentum fraction. So roughly speaking, you can think of this as being, you can think of this as having, say, if I want to go back to the previous slide where I have the Feynman diagram, you can think of having a gluon with momentum x1, p1, where p1 is the momentum of the parent proton, and likewise x2, p2. And these are 4 momenta, of course, but this is a strict proportionality, so this is just a number. And then you calculate the Feynman diagram, and there will be some relation between this x1, x2, and the energy momentum of your final state, whatever that is. Okay, so it's an indirect relation. It's an integral. Yep. Yes. Right. Summation, because you have various kinds of constituents. So this is the gluon, but the, oh, sorry.
So is the sigma, added sigma is.
What you measure.
Yes.
Yes.
Okay, so that's like on my y equals x.
So, right. So this is what, oops. That's right.
We have those, and it's the m's in this.
Very good. Exactly. So this guy is calculated from perturbation theory currently to very high accuracy. This is measured, and this is what you want to get. So back to the Monte Carlo. So we first turn the data into a Monte Carlo representation of the data. And then we are back to the question in the sense that then we have, I mean, the data are data for each of the 5,000 observables that we've been talking about. Say, well, we don't use the Higgs yet, but say the W cross section with a certain angle, you know, W detected at a certain angle in the lab. Okay, and that we calculate by folding some underlying neural net where there is one, well, or I'll get into the details, but like I say, there is a neural net that tells you what is the value of the PDF for all X, okay? And that gives us a prediction, and we have an ensemble of data replicas. We minimize some loss function, starting with completely random neural nets, which gives us a neural net which corresponds to all the PDFs for that data replica. And then because we have an ensemble of data replicas, we end up with an ensemble of neural net replicas or PDF replicas, if you wish, that we can use to calculate central values, uncertainties, and covariances in PDF space by simply doing statistics over the final Monte Carlo ensemble. So that's a basic idea. Yes, yeah. Next slide. Okay, so this was our old, starting 2000, so 2002 was a proof of concept, 2006, I guess, was the first actual PDFs, and from then, so 2006 to 2021, so 15 years, we picked an architecture which was general enough, I'll give more details, but we had this kind of architecture. So we had a neural net with 2 hidden layers. You see the architecture, so we started with a limited parameterization where we only parameterized up, down, quark and anti-quark and the gluon, and then we started, you know, getting more detailed also because there were more data. And in the end, in 2021, we had 8 PDFs. Up, down, strange, anti-up, anti-down, anti-strange, total charm, and gluon, and forget heavier quarks. The PDFs are pre-processed neural nets. There is a certain procedure to determine the pre-processing that I can get into later, but it's a kind of technical now. And we did genetic minimization of a loss function that was basically the chi-square to the data. we had a sequence of improvements of the methodology where in the end we had nodal mutation. Earlier we had point mutation. In the end we had a single epoch, while previously we had different epochs with different mutation rates. In order to determine stopping, we use cross-validation, where each replica is, each data replica is divided in a different way into a training and validation set. And of course, we train on the training set, we stop on validation. We are aware of the, or we became aware of the problem of yesterday's talk. So at some point, I guess in 2013 or something like that, we replaced look-back stopping with, so previously we stopped when the validation steps started going up, but then we started, instead of going on to a very long training length and then looking back at the absolute minimum, because we realized that things could go up and down again. And of course, that also depended on having a more efficient code, because in the beginning, going to a very long training and then looking back was beyond our capabilities. So this was up to 2021, and now we come to the interesting part, which is what we've been doing for the last several years. When well, I had this ERC grant, and the idea was to completely restate the problem as an actual machine learning problem. So the idea was that instead of having this kind of hand-picked neural net architecture and methodology that I briefly summarized in the previous slide, which was based on experience, 10 or 15 years of development, gradual improvements, we should do this systematically in a computer-driven way, as opposed to based on experience. So this also corresponded to a slight change in philosophy in minimization. I mean, previously we always used genetic minimization, basically because we were afraid that otherwise we'd end up being trapped in minima that were driven by our subjective choices, while we now switch to great extent with the idea of exploring a wide variety of minimizations and architectures. So the idea of hyper-optimizing the entire methodology in such a way that we are sure that we are not getting trapped into some local choice, but then we can aim at a much higher precision and accuracy. Now, this required completely restructuring our code base. Well, first of all, we switched from C++ that had replaced the original Fortran in the 2010s, I guess. So we had to switch to Python so that we could use Keras and TensorFlow libraries. And more importantly, the whole code was restructured in a series of independent layers or blocks in such a way that the hyper-optimization could change each aspect of the methodology without influencing the rest. This new code structure was not only much more flexible, but it's also much faster. And what used to run in 15 hours now runs in 40 minutes on a CPU and in 6-7 minutes on a GPU. And that was the time required to train one neural net replica. Now, the general structure of the code, or the general philosophy, remains the same. In other words, we start from data replicas, we produce, we start from data, we produce data replicas. From data replicas, we determine PDF replicas. Each PDF replica is a pre-processed neural net, and the neural nets are what we get as basic result. We have cross-validation with a random training validation split, and we now have a patience algorithm instead of the look back, which is a bit more efficient, and the lowest validation chi-square gives the optimal fit. And this is the final structure of the code. And as I mentioned, I wouldn't say everything, but lots of aspects, both of the basic underlying neural net and the minimizer, are hyper-optimized. So specifically, we vary number of layers, size of each layer, activation function, initialization, the choice of optimizer. I mean, we use deterministic minimizers, but we have a variety, ADA, delta, ADAM, and so on, learning rate, stopping patients, and some aspects like positivity multiplier, which are more specific to the specific PDF problem. And what this figure is supposed to illustrate is a typical hyper-optimization scan, where each point here is a fit, and each point here, the stars correspond to what is represented. So there are a few things that are not shown here. So a point here will be, some learning rate, some choice of initializer, some choice of activation function, some choice of optimizer. Some of them are discrete, obviously, and some are continuous, like the positivity multiplier. And we do parameter scan with Bayesian updating, where the figure of merit, which is optimized, is the validation chi-square. Okay, and at the end of the day, when we tried this, it was a disaster. So the first time we tried it, it was a disaster. So this is illustrated by this plot. Let me explain. So this plot compares what we had with the previous methodology on a subset of data, which is deep inelastic scattering, a particular physics phenomenon. So this was a pre-existing PDF set. It's a bit wiggly, but these wiggles are finite size effects. If we had more and more replicas, the things would smoothen out. But then we tried with a new overlearned methodology, the optimal fantastic thing, and we got this incredibly, horribly wiggly thing. So something which is obviously overfitted, and then you ask, these wiggles do not go away with, in fact, they become worse with increasing number of replicas. So what's going on here? Now, what's going on here is the following, that, the underlying methodology is cross-validation. So when we do a fit, we aim at the low loss function for the training set. We have a validation set as a quality control, and that monitors the quality of the fit and avoids fitting the noise in the training set, obviously. Now we put this thing inside a bigger box. The bigger box is the hyper-optimization. Now the bigger box has as a target a low loss function for the validation, but it does not have a quality control. And therefore, it's prone to overfitting. And why is it prone to overfitting? Well, it's prone to overfitting because even though you're fitting training and you're optimizing validation, you always have correlations between, hidden correlations between training and validation. For example, as I said, we calculate from Feynman diagrams, but that means we calculate at a fixed order in perturbation theory. Now, the missing higher order contributions will be common to the training and validation set. And then, of course, you'll end up overlearning these hidden correlated things. And that's a very simple example, but there are subtle ones and also some which are related to experiment. So what's the solution? Well, the solution is obviously to introduce quality control also for the hyper-optimization. I introduce a test set. In other words, you want to have some set of data which is not used at all in the whole procedure, such that you check that the quality of the agreement to the test set does not deteriorate, and only then you accept the methodology. And once you start to do this, so this is the same plot as I showed before with the older methodology with wiggles that eventually disappear, the new methodology with horrible overfitting wiggles. After you introduce the test set, you get the green thing. So not only the wiggles have disappeared, but even the finite size wiggles have disappeared. So you get a really much better methodology. Now, of course, you may object, fine, but then you handpick the test set. Yes, that's correct. And that's why this is not, once we realized that this was a problem, we turned to a better solution, which is maybe not so different, but it's philosophically better, which is to use k-folding, which means that we take the data, we divide them into n folds, so subsets. So let's say one has chorus neutrino deep inelastic scattering data, and the other has Nutev neutrino deep inelastic scattering data, because they're different experiments. They're not related, but they test the same aspect of the PDF because they're the same physical process. And then we fit using n-1 folds. I'm sorry. we fit using, and we hyper-optimize rather, using n-1 folds, and we monitor the loss function for the fold which has not been used for minimization. And then we pick the methodology which has the best behavior of the non-included fold, where best behavior can be defined in various ways, like the best average or the best worst, and we check that it doesn't really make a difference which one we pick. And well, sorry, I guess I wanted to show you this first. And once you do this, so red was the one with the test set, green is the one with the K-folding. So this shows that the difference between the hand-picked test set and the K-folding is not that big, but as I said, philosophically is much better. And anyway, it is a little better. We get slightly smaller uncertainty and slightly smoother behavior. And in case you're curious, I'm listing here the current 4 folds with the list of experiments that are included in each of the folds, and we ran various stability checks. So I guess I'm almost running out of time. I have
No, but you have all the time that you want.
okay.
So the lunch is the only barrier.
Yeah, okay.
So,
very good. So yeah, but I don't want you to die or fall asleep or whatever. Anyway,
No.
so this is the
didn't-
methodology we
Stefano,
finally get.
You didn't say that explicitly,
Yes.
but so this splitting of the data you do only for the hyperparameter optimization. Then you will get the PDF from all the data afterwards.
Right. So yeah. So
So you
so
use
this is the hyper optimization. Right.
Okay,
So
and
this
then you use all the data.
then we use all the data, except that when we do a fit, all the data are used in cross-validation. So we use 50% of the data, but then 50% for each replica in a way that is randomly divided. Actually, right now, I guess we use 75% because in the end, we realized that the amount of data is so copious that even with 25% validation, we still control very well over learning. So we don't need 50-50. And we check that there is, unless one goes and looks at very specific things. Yeah, but okay, the bottom line is that there isn't much difference between 50% and 75%.
Okay, I try. I mean, yesterday we learned that you have this overfitting problem, but then at some point, the more parameters you add, the better it gets.
Yeah. So as I said, previously, among the hyper optimization parameters, we have, so at some, as I said, we were aware of this, and that's why we switched from increasing gradient to look back long ago. Now we are one step further because among the hyper optimization parameters, there is, if I can get there, there is the stopping patience. The stopping patience is how much if the chi-square of the validation starts increasing, you keep going anyway, and then this is hyper optimized. So so if it goes down again, you know how much you have to go on before you see it going down again.
How many hyperparameters versus how many parameters in the smaller box?
So I have to go back to the previous slide, which is where I. Oops, sorry.
In your box in the box.
Right. So this is, yeah.
Oh.
Okay, yeah, this is where it was left. So this is, so these are the hyperparameters, and these are the parameters, if you wish. Now, our default hyper-optimized methodology is like this. So we have about 800 parameters. And hyperparameters, I'm not sure I listed them all. There are a few more that I did not list here, but these are the main ones, the architecture. So in the old days, we had one neural net per PDF. Now we have one single big neural net which produces output for all PDFs. We can choose to produce output for different linear combination of PDFs, and as a matter of fact, we check that the results are independent. I mean, some choices are have some advantages. So, for example, you may think that it's more natural to have up, anti-up, down, anti-down, but it's in fact more natural to have some linear combinations which are the eigenstates of perturbative evolution equations, which is, well, kind of technical, but anyway. Anyway, linear combinations. We have two input nodes, x and log x. If given time, I'll comment on this at the very end. Roughly speaking, because PDFs have two regions, one where they behave like linearly and the other logarithmically, even though strictly speaking, this is redundant. But and so one way of improving would be to get rid of this redundancy. And so, for example, this column and this column compare the hyper-optimized architecture that we get with our default basis, which is the one in red here, and the different basis, meaning different linear combinations as output. And I guess the interesting thing is that even though the outputs are perfectly compatible, in the end we get the same results with uncertainties, the architectures are very different. And in fact, the flavor basis here demands a much larger number of parameters, which is related to the fact that, as I was mentioning, this other basis is more natural. I mean, crudely speaking, what happens is that, how should I say, once you turn on perturbative corrections, you get that as the resolution varies, the behavior of the PDFs at small and large x is driven by these perturbative corrections, and the eigenvectors of the matrix of these corrections are the ones that have a particular given behavior, and these are therefore the preferred solutions. Otherwise, if you take linear combinations, you must have a linear combination of things that end up behaving in different ways. So you have to kind of fine-tune a superposition of things. So it's harder, and the neural net manages to do it, but it needs a bigger neural net. And okay, so you see what.
Can I ask a question at this
Yeah.
point? So you're right, we have 803 parameters, and these are still by neural network standards. This is a tiny network. It's basically like a.
Yeah.
I mean, you can. I guess in C++ you had it written down in a line of code. You are like tiny thingy instead of layers. Anyway, my question was, if you have like n particles where n is like 8 or whatever, have you explored, and has anyone explored just literally tabulating the PDFs and having parameters being like the PDF of this particle with this X, the PDF of this particle with this X, blah, blah, blah. And this would, if you just have 100 points, like a grid in X, it would, kind of have the same number of parameters as the network. And then I can see like a bunch of like the activation function, the number of layers, blah, 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 as hyperparameters just disappearing.
Yeah.
And the whole analysis being, a little bit more robust, because then you can directly impose constraints like this has to sum, actually this has to kind of not be negative, blah blah blah.
Yeah.
So I mean, what is the advantage of using a neural network over a much simpler, more direct approach to modeling?
Okay, so a simpler, more direct approach is possible, and I guess Alessandro gave a talk about that at the workshop 2 weeks ago. But so the advantage of the neural net, of course, is that the neural net has a built-in how should I say it, regularization or smoothness. In other words, there are some desirable physical features that we want the final result to display, and which naturally come out from the neural net. While if we just parameterize the grid of points, so for example, you want to have some kind of natural correlation length. And what the neural net does is it automatically implements this correlation length, and if you wish, the outcome or the main point of this whole hyper-optimization is to have an architecture which reproduces the natural say regularization of outputs that is suggested by the information that we have at hand now. In other words, in some regions of space, don't forget that the PDFs are related to observables through a convolution. So it's not like we have the PDF in one point. I mean, one observable controls some integral over the PDF, which is roughly localized. But for example, one thing that we did is to try and have a a fit in which I'll get to that in the next slide, but a closure test where we assume an underlying form of a PDF, and then we generate data with zero uncertainty, and then we can have a fit with a loss function, chi-square equals 0, right? It's going through all data points. Even so, the PDFs have an uncertainty because, and they have an uncertainty everywhere because there isn't it's not like, it's not like you measure something so you have zero uncertainty and you have an interpolation in between. No, because you have an integral, a convolution integral. So you end up anyway having a bunch of curves like this once you go through the convolution. So it's and then what the neural net does is it naturally implements the sort of correlation length. Now, of course, in the limit of infinite size, a neural net would be like a Gaussian process, and then the result would depend on what you pick for the kernel. And we actually tried to, but then we see that according to which kernel we pick, we can get almost anything, while the neural net seems to produce naturally the.
By the way, people in my department, I can confirm that their job is to kind of actually calculate the intrinsic kernel that a particular neural network architecture represents,
Yes.
and it depends on like the number of neurons and the kind of the non-linearity, and blah, blah. So I mean, I would claim that you're doing a neural network actually chooses a kernel, like imposes
I agree.
be actually rephrased in this kind of
I completely agree.
Just mention.
That's exactly what I was trying to say, actually. Yeah.
So what we are actually doing is to try to infer the PDF distribution at the moment using a Gaussian process as a prior, and just imposing a likelihood and the Bayesian of data. So we can do it with the approximately Gaussian inference, because the problem is that here we have functions, and the functions, even if you choose point of the functions, they enter not only linearly in the data that we have. So we don't have only linear transformation, only we have even quadratic transformation and so on. So it's not completely trivial. We can do a Gaussian approximation, or we can do direct sampling with something like Monte Carlo or something like that. Problem is that at the moment we are trying, and we believe, we are confident that sooner or later we will get it. But in a few months that we have tried, we are not passing the closure test, in the sense that our hyperoptimization cannot get a correct correlation length or better. It's borderline on the correlation length uncertainty the moment that we impose something inside. Instead, the neural network is passing a closure test out of the box.
Yeah. So I guess the short answer is that indeed we would like to do it, but that's in the making.
Yeah,
I should add some interesting information, which is, since you mentioned the number of parameters. I mean, one thing that we've done is, so even though in the end our deliverable is a set of replicas, a set of a Monte Carlo set of neural nets, sometimes experimental collaborations prefer a multi-Gaussian representation of the answer. So what we do is we fit a multi-Gaussian, and the way we do that is by simply sampling each PDF at one point, and then we perform a singular value decomposition on the answer, and then we pick a number of the leading eigen vectors that produce a multi-Gaussian approximation to the answer, which is good to a given accuracy. And at the end of the day, I guess by the central limit theorem, our results are Gaussian almost everywhere except at the kinematic boundaries, for example, when you have things that are squeezed. And then we can check how many eigenvectors do we need, because that's the number of independent parameters. So if we want to do all the PDFs everywhere where they are well determined, 100 eigenvectors, 100 Hessian eigenvectors is enough. But if we want to do, say, leading LHC processes, so for example, let's say Higgs WZ production, I mean, say the 10 most important observables at the LHC, a dozen eigenvalues is enough. So and in fact we have a nice piece of code where you list the processes, and that automatically determines the number of eigenvectors you want, which is in some sense going in the direction you say, because then we can unfold. I mean, this then we can say which points in which PDFs have been selected because we know which eigenvectors we are looking at. That, if you wish, establishes directly a correlation between LHC observables and the PDF sample at some point. But that's done a posteriori by doing, taking our final answer, projecting it into a Hessian representation, and then doing SVD on it. And then we discover that we have a small number of parameters. So 800 is really over parameterized. Okay, so now since Alessandro mentioned, I mean, in the last 10 minutes, the words closure test have been mentioned several times. So let me get to the almost last part of my talk, which is how do we make sure that we are getting the right answer. So we have a couple validation methods. One is closure test. So closure test, the idea is simple. We assume that the underlying PDF is something, we generate data, and then we run the whole procedure on these data and then check whether we get the right answer. Okay, so we take as a underlying truth, I don't know, some random PDF replica or some PDF determinations from some other group. It doesn't really matter. We generate data with, as if they were real data with uncertainties and correlations, but the data that experiments would measure if that PDF were the truth, and also assuming that the theory is exact. So we have no other uncertainties in the process but the data uncertainty, and then we just run the whole methodology and we go and look at the final answer, and we can repeat this many times as if, in a frequentist way, if you wish. We restart the universe, we regenerate data, and we rerun the procedure, and then we can check. I know that's 68% of the times the true gluon is within 1 sigma of the gluon we get, for example. Or we can check that the bias variance ratio is equal to 1. And well, this is the check we've done, and this is a comparison to a univariate Gaussian. So, we are satisfied, we've satisfied ourselves that at least in this simplified setting, we get the right answer. Of course, the real world is more complicated because of what we heard in yesterday's talk. Say the experiments have inconsistencies. So, for example, one thing we are looking at is repeat the closure test, but now putting some inconsistency in the data and see what happens. And I hope, if I come back next year, in 2 years, I can show you results for that. The other thing is, I mentioned that interpolation is a problem, but extrapolation is an even more serious problem. So how do we check uncertainties a closure test checks uncertainties in interpolation. I check that if I predict a data point with 1 sigma uncertainty, the real value of the data point is inside my 1 sigma band 68% of the time. But what about extrapolation? So we had this idea of doing what we call a future test. We called it a future test based on, what I was mentioning earlier, old experiments where results came as a surprise. So for example, I mentioned when Hera was turned on, the behavior of the structure function was different from what is expected. So, we asked ourselves, well, what if predicted what Hera should find based on pre-Hera experiments? In other words, we perform a PDF fit using only the data that were available in 1991, say. Of course, that's kind of arbitrary, but just for fun. Right? Then we run our current methodology. So it's a bit of a cheat because the methodology is hyper-optimized to current data. But we take this new modern hyper-optimized methodology and we fit 1991 data with it. Of course, we'll get much bigger uncertainties because there's much less information. So if we were just to compute the loss function with a central value with Hera data that came 10 years later, it would be horrible. But then we put in the PDF uncertainties and we see what happens. And lo and behold, for example, if we do a pre-Hera fit, we get a chi-square per data point of 24 if we don't include the uncertainty, but then it goes down to 1.1 once we put in the PDF uncertainty, which means that we have this tenfold increase of the uncertainty, which exactly accounts for the missing information. And we did this exercise in various ways. Okay. Right. So this this is the final result, and this is the comparison of the current best result we have, which was published in preprint form about a year ago and in paper form a few months later, compared to the previous PDF set from our group. The previous set was not using all this hyper-optimized thing. And the bottom line is that, as I was mentioning in the very beginning, uncertainties are by and large down by a factor. I mean, typically we had 4 or 5% PDF uncertainties. Now we have 1% PDF uncertainties, which is what people at the LHC or experiments at the LHC would like. And if I could stop here actually, but maybe I can go on just for a few minutes to mention that there are a few more aspects where we used fun machine learning things. One is for delivery. So I mentioned that sometimes we do this fit of a multi-Gaussian to our final result. Another thing that we do is compression. So instead of having 1,000 replicas, we want to pick a subset of replicas that reproduces the features of the 1,000 replicas. And this we did with a genetic algorithm. So like, you know, this is the covariance matrix. This is a heat map for the covariance matrix between PDFs, determine 1,000 replicas and an optimized set of 50 replicas. So for example, say red here means that the up bar quark and the S quark for this X value, which you cannot really read, are anti-correlated to 80% for some reason. And then, I mean, you visually see that with 50 replicas, we get something which is very similar to the 1,000 replica, while if you picked 50 random replicas, it would be horrible. It would be all over the place. And this is something which we did long ago, but recently we had the idea of improving this with GANs. In other words, the set of replicas that we compress. So we start with, say, 1,000 replicas, and we generate lots of fake replicas. And then we compress the set that includes both the original true replicas and the fake replicas. And then, of course, you know, the fake replicas have many more variations. So you can pick a subset that is closer to the original with a smaller set of replicas. And of course, you know, you don't have to worry too much about the GAN doing crazy things, because if a replica is crazy, it simply won't be picked once you optimize to your set. And this shows well, this particular performance. So this is the value of the loss function. So this is a size of the compressed set for a certain value of the loss function. And so let's say, okay, so for example, if you want to have this kind of accuracy here, you need 170 replicas in your final compressed set, while if you look at the red curve here, it intersects here, so you're down to 90 or something. So you have the number of replicas you need in the compressed set for fixed accuracy by having enlarged your starting set with the GAN generated things. Okay, so this was it. And then new developments. I mean, there are various things we are thinking about. One is getting rid of the X log X. And so I guess this is a bit technical. Maybe I should cut it down and I can give more details if people are really interested. So right now we have this pre-processed form, and we have two inputs, X and log X, and we determine the pre-processing function in a kind of slightly contrived way. And there is this some idea that using a ECDF rescaling of the input, we can have just one single input instead of X and log X and get similar results. And then also we'd like to automatize the choice of folds that we use in K-folding, for which we need a measure of an objective measure of overfitting. And then we have more more ideas, one of which was discussed by Alessandro, and that's what he's working on right now, namely to go beyond neural nets, as mentioned in the previous discussion. And so this is really the end of my talk. And of course, this is very important thing. I was forgetting this. Everything which we do is open source. So you can get everything. I mean, the full code is public, including the whole hyperoptimization, the plotting routines, the theory part. We got permission from people whose calculations we are using to publish their code, or their output. So everything can be downloaded from well, you can Google NNPDF, and then it will direct you to this place here. Run cards, documentation, well, there's a paper to document this. There will be, yeah, that was stupid of myself. I forgot to mention this here. 1 year from, a little less than 1 year from now, there will be a school at the Como, Lake Como School for Advanced Studies, mostly based on, you know, having hands-on tutorials on our code. And this has been done thanks to the fact that many people have been working on this project. This is a picture taken at our last collaboration meeting, which was a few weeks ago. There are a few people here who are guests, but most of the people in this picture are members of the collaboration, and in particular, all the hyper-optimization and you know, the more recent machine learning aspects have been done by my group in Milan, which is shown here. Now some people has left, but this is the integrated group over the 5 years of the EFC grant, about 10 people. And well, project is ending now in a few months, so this is not going to grow substantially. And well, Alessandro is sitting here in the front row, and there are a few more people. Okay, thank you very much.
Yeah, okay. Yeah. Okay, got it. Yeah, thanks for the very interesting talk. I mean, I was wondering about the final output, right? I mean, when you want to do simulation, I suppose you provide, what do you provide for MathGraph, for instance? You provide grids of possible points, yeah?
Yeah. So what we've been working hard on various kinds of fast grid interfaces. So you know, the default, the basic thing that we provide are PDFs in LHA PDF format, which is a standard format with which PDFs are delivered on a dedicated server. A part of the project here, which you can get from our website, is actually, well, I mean, you can see it here, right? LHA PDF grids are our final deliverable, but a part of the project is actually to have grid interfaces to all the processes that we use, which are part of what we make public. So in particular, we are working towards a universal, so at present, not all processes are so, you know, public codes that compute results to a given perturbative accuracy are not available for the same accuracy for all processes. So what we are aiming to is to have a common grid interface such that we can get a next to next leading order QCD plus next to leading order electroweak computation in universal grid format for all processes that we are using in our PDF determination, and can therefore be used by anyone else to compute their predictions. So we are working towards that direction together with the Matrix group, and maybe you're familiar with them, which includes a wide variety of processes, and now also with NNLO Jet++, which includes some processes which Matrix does not include, specifically jets or W plus jet. You know, at that point, we should have not only the LHA PDF grids, but also those interfaced to a fast grid interface for the computation of physical processes.
I was wondering, I mean, you mentioned very fast that you are training also GANs, right? So, I mean, I was wondering if you actually provide generators at some point.
I didn't get you, sorry.
Yeah.
Yes?
Yeah, I mean, you can, in principle, provide now generators, no? So you can sample for a simulation instead of the grid is something that makes sense.
Sorry, generator, you mean?
The GAN such that people don't do
Oh, the GAN, yeah.
That's a estimator.
Yeah, I guess we could. Actually, I guess the GANs are not yet part of the publicly available part of the code, right? Because we have not, I'm not sure, because yeah, compressor is, but I'm not sure about the GANs because they have not been used in any official PDF release.
The main point is that most of the people are not interested in any other output format than the PDF. So this is one part of the format is not only going to, and then we have others for another PDF. And since people are doing that one, yeah.
Yeah, I mean, typically these CERN experimental collaborations, Atlas, TMS, they have these huge, say, detector simulations, which have one single LHA PDF interface. And in fact, they are very reluctant to replace a PDF set with a more recent one, let alone change the underlying format. So, for example, at present, our most widely used PDF set is still an NPDF 3.0, I guess, which is from and even an NPDF 2.3, which is from 2012, I guess, because experimental collaborate. I mean, Atlas and CMS are like a big ocean liner or a tanker ship. I mean, it steers very slowly.
It will be a nice change of paradigm if you can provide an explicitly
Yeah, but that's something we consider. We even discussed whether we should propose a new data format to replace LHA PDF, but it's very difficult. Because...
Yeah, even the proposal of substituting the one output as the transfer down to the server, but because that is the original output of the filter without any more than installation. And we could do it, but we want to do it. So it's the big point.
we need to prove that it's somehow better to do this.
It is not.
But then we stick with that. Okay, thanks.
So, as we were discussing before, you are building in some implicitly some smoothness, or if you want, some correlation between the value of the PDF at different axes.
Of course, yes.
And you're doing this in a completely data-driven manner.
Yes.
That is your optimization at the end.
Exactly.
is doing. Okay.
Yes. Yeah. So we impose in
like,
general, as a matter of principle, we impose all the constraints that we know to follow from fundamental physical principles, like, say, momentum conservation, but we do not impose any model constraint or smoothness or whatever, and we let everything be data.
Let's say you find the smoothest possibility that is compatible with the data, but in a non-explicit manner.
That's right. That's right. So, for example, that's a very good point.
I wanted to say that from Qt, at x equal to 1/2 narrow, 1 per mil narrowness, where it comes from, right? That's a very good theory prejudice to be put in, for instance, right? But you don't do this explicitly. You
that's right. Absolutely, absolutely. No, that's an extremely good question, and maybe I should mention this because this is something that we've been discussing recently. So there are some people from a competing group who have shown that they can take linear combination of our results, and by taking linear combination of our results, they can produce some PDF configurations that have the same loss function as we have, but in the plane that I was showing in the very beginning. Let's see whether I can get there in a finite amount of time. So the plane of the Higgs cross-section and the Z cross-section. Yeah, I'm almost there. Okay, too much. 1, 2, 3. Okay. Right, so they can produce configurations that say sit down here. So for us would be, I mean, you can see how big this is. So down here would be 4 or 5 sigma, and yet have the same value of the loss function that we get, right? And then they say, they fit a functional form. So they say, well, we have an absolute minimum and then the chi-square goes up. And how come you have configurations that are far out there? Why are they disfavored by your fit, despite the fact that their chi-square is the same? And, we went and looked and we discover that once you look at the, say, the gluon PDF, or X times the gluon, let's say we have a behavior which is something like this, and actually no, I got it wrong. We have a behavior which is something like this, and let's say the data with some uncertainty, and let's say the data stop more or less here, and these configurations, sorry, it's like this, and then it has a peak here. And the data stop here, and their configurations down here do something like this. I'm exaggerating, but so they introduce some feature which is in a region where there is no data. And so the data are here, and here there is no data. And this is, say, an NPDF, and this is a candidate. Okay, and so the configurations that produce a cross section, which is for us disfavored by many. Of course, you know, eventually, if we not run a large enough number of replicas, we'll get some PDF that looks like that. But for us, it's very unlikely.
So sorry, just that region. When you say data is not included cross section of X.
So the PDF that does this, then here does something like this. So it's slightly higher here. So in the data region, it produces something which for us is excluded by many sigma, but the cost is to introduce this extra structure in a region where there is no
minimizes the loss by that negative thing.
It minimizes, I mean, exactly. I mean, so for example, I told you that there's this constraint that the integral must be the same, so they can get an extra little bit here at the price of having something that goes down, and therefore, you know, there's a smaller contribution to the integral from this region, which then, however, requires doing this kind of gymnastics.
This is not penalized by your loss. There's not a regularization in your loss that penalizes that.
Exactly. So that's why I'm pointing this out. So there is nothing in our loss that penalizes that. It's that the methodology, obviously the methodology which was based on the data, does not like to do wiggles in the region where there is no information that requires such a wiggle. But there is nothing explicitly there in the loss. Yeah, that's right. Yeah, so yeah. So you're absolutely right. So locally, this thing is within our uncertainty band, but the global prediction that you get from that PDF is that's right. Yes.
A related question. When you do your closure test, no?
Yeah.
Should this fail if you start from a PDF that is not smooth enough, let's say?
That's also a very good question. So we tried to do for example, in this case, we tried to do a closure test using this wiggly thing as an input. And so we can get a low chi-square, so we can get a good quality fit, but our good quality fit tends not to reproduce the wiggle. Our interpretation. Sorry.
Then at the end it fails because you put a wiggle.
It doesn't fail because the wiggle is outside the data region, and
exactly. So better to do it with the wiggle, so with something in the data region. Suppose I put a delta function.
So let's say, so it's certainly true that our methodology is hyper optimized on the current data. So if the current data were all wrong, our hyper optimized methodology would be different, but that's very unlikely. On the other hand, if as the data region extends, there are very different new structures in the new regions which are not covered by present data. I guess, yes, we would need an extra hyper optimization. I mean, in other words, remember the future test, right? So if we run a fit on very old data with the current hyper-optimized methodology, we get uncertainties which are big enough. It is possible that if we had that we didn't try, I mean, but that would be interesting. If we had hyper-optimized on 1992 data, then we'd get a methodology which is rather stiffer, and then maybe that would not accommodate current data. On the other hand, for all we know, now the data coverage is such that it's unlikely that there are new structures that appear outside.
And my question was more to try to make explicit the regularization that you are implicitly doing.
Yeah.
It's when there is when this regularization is not there. I don't know, with this regularity, sorry, is not there. You see what I'm saying?
Yeah. I wonder whether I have the clip norm.
Yeah, but in fact, this is the part that you were saying before, that the neural network is learning very live the data itself. So if the data require more interpolation, the neural network is able to provide.
So I mean, optimization is effectively doing this, but it's doing.
Yeah.
I would like to see that happening somehow. That is.
Each set of hyper practice imposes a certain magic prior on non-data strength.
Yes, this is very, very interesting, very big, and I would like to see that this is happening.
Yeah. Yeah. So for example, one thing that we tried is we take our final hyper-optimized result and we screw up some parameters. So for example, there's one parameter which is called clip norm that cuts off the rate of descent of the gradient descent algorithm. And if you remove that, then you can get a very rapid descent. And if you do that, you start getting results that look like the red curve here as compared to the green curve. So you start to get big jumps. And of course, the value of clip norm that we get was not picked by us. Matter of fact, we had Alessandro is laughing because at some point we had a bug in our code such that basically the line which fixed norm was commented out, and we got these very funny results, and we didn't understand why, and that's because we thought that was hyper optimized while it wasn't, and then we'd start getting these wiggly things. But of course, if the data were wiggly, presumably the hyper opt would choose a larger value of, and then we'd allow for. So that's a very obvious example of one hyperparameter that controls some very visible aspect and which is determined by the hyper optimization comparing results to data.
The feel of your talk is that you're very happy with what you have. And so what is is there like some real serious problem in your mind that you need to go and do, or is it like almost done effectively for what the community needs?
Well, that's a good question. So I guess there are two aspects of the answer to the question. I mean, one is there are obvious things that are in the line of incremental development. I mean, the general push at the LHC is to do precision physics in the hope of discovering dark matter and so on. And in that sense, even small improvements are very desirable. So, for example, if we can control things like the impact of data inconsistencies or theory inconsistency on the final answer, a bit in the vein of yesterday's talk. That's something. For example, one thing we're looking at now is introduce disenclosure tests and see how the neural net deals with that. And so that's an example of kind of incremental development. The more fundamental development instead is the one of the previous questions, namely whether we can kind of open up the model and understand why it is doing what it is doing, namely, for example, what is the, is it a Gaussian process, and if yes, at which current, what is the corresponding kernel that we get out of it? What is the specific aspect of the data which is controlling some feature of the answer? And of course, that would be interesting not only because it, it would open up the black box a little bit, but also because it would start maybe telling us something about the underlying physics. I mean, at the end of the day, that's related to the questions that were asked in the beginning of the talk. I mean, why do you pick x to the alpha times 1 minus x to the beta? Are we actually, is the neural net actually reflecting some functional form which is different and this related to some physical feature. Now everything for us is data driven, but at the end of the day we are doing physics, so we'd like to know what the structure of the proton is. So for example, we now have indications that the large X behavior 1 minus X to some fixed power is not what the data seem to suggest. I don't know, maybe the correct behavior is log 1 over X to some power, which of course, if you Taylor expand it about X equal 1 is 1 minus X, but log 1 over X, as soon as you get away, is different. So maybe that's what the neural net is trying to tell us, but we don't know. So.
Yeah, and for example, one of the things about this exercise that we learned is that if someone is telling us, okay, you're not getting this, and this is completely weird, and this is because your architecture, your methodology is too stiff, and you cannot get it. And we can prove, no, that's wrong. So if it was there, we could get it. That's fine. Then comes the answer. Then why you're not getting it? And the answer to this question is complicated.
Exactly.
And we cannot tell.
That's a bit like the question Andrea was asking earlier. I mean, can you tell which regularization are you imposing? And we are not imposing any regularization, but effectively, at the end of the day, the methodology that we get out of the hyperopt is imposing some regularization. So can we interpret this answer? I mean, so it's, if you wish, the interpretability problem is so we are very happy of the phenomenology, but now we'd like to understand a bit better what's going on.
A slightly related, just to close off like this, a slightly related thing. I'm going to mention a word which kind of doesn't go together with particle physics too much. Are you interested in doing, you know, robust, so how do you call this, actual Bayesian inference?
This is exactly
okay,
what.
but you know, have you tried? There's one other aspect, you know, the Gaussian process, the prior. The thing which strikes me the most, you know, in Bayesian terms is this, you know, data resampling from the likelihood, which is something which, you know, Bayes would kind of turn around in his grave if you ever did that and claim that you're getting. But I mean, I could see how this could lead to Bayesian interpretable results. The point is, there have been recently, also in particle physics, a bunch of methods which, so to me, your problem now seems to be that you have a very limited data set, that you are kind of training a neural network on your experimental data, fine. But recently there have been methods in which you, I mean, because your problem is actually to infer parameters from that data and not to, you know, train an emulator or whatever for that data. So there have been methods in which you aim to infer, do exactly this, infer parameters from data in the Bayesian sense, with neural networks, so that you keep all your, you know, niceness and flexibility, but you don't train on the data, you train on a model. And then on the model, you completely control. And then it's completely interpretable. And then you just evaluate on that data. And so my question is, how much you want to be rigorously Bayesian? And if you do want, I mean, there are pretty nice methods, recent neural methods for doing that kind of thing. One of them actually relates to, you know, to Gaussian process and inferring the parameters of the Gaussian process.
In particular, the idea is, if possible, we will really do Bayesian inference, just pick our prior, that's it, with the hyperparameters and so on. We pick the likelihood, and we just get a posterior. Just sampling the posterior as it is.
Yeah. So let me tell you, you know, some history. I mean, this whole thing was partly born because in I think mid-90s, David Kossauer, with a couple of collaborators, was unsatisfied with these fitting functional forms. So he made the following suggestion: why don't we use a purely Bayesian approach, whereby we start with some prior, and as a prior we can take any PDF determination which is available now. I mean, then they were very poor. And then we just start including data then we generate a bunch of Monte Carlo replicas of PDFs, and then we use Bayesian inference to prune down the set of Monte Carlo replicas in order to get a distribution, a posterior distribution. Okay, now that didn't work for some reason that no one knew at the time. So he went on for a few years and then he just dropped the project. We later understood what was the problem. The problem is the following, that sometimes we actually do include some experiment by Bayesian reweighting. So we start with, I don't know, 1,000 replicas, and if we want to include just one experiment, we start with our distribution size from a global fit. And instead of adding this new experiment and refitting, we actually use it as a reweighting to produce a posterior after including that experiment with Bayes' theorem. And what happens, obviously, is that the replicas in your original set that are most unlikely with respect to the new set gets deweighted, obviously. So you end up with a weighted set, and from this weighted set, you can compute an effective number of replicas. I mean, you could reweight or re-deweight the final set in order to have an equal importance sampling with a new set, and then see how many replicas you have in the reweighted set. And what we discover is that if we start, say, with 1,000 PDF replicas, even relatively small size experiments like 10 or 20 data points immediately drastically reduce the number of replicas from 1,000 to, I don't know, 50 or 60 or something like that. So So the reason why Kossauer's idea did not work is that he would have to start with 10 million replicas and then do Bayesian reweighting to end up with a few hundred or maybe 100 or maybe 50 final replicas. In other words, the problem is that the space of functions is very big, obviously, and most of them are going to be completely excluded, and therefore you have to start with some huge space in order to apply, if you do it in the naivest way, which is just to have this. Of course, the crucial thing is if you do it in the naivest way. So if there's a clever way of doing it, which is what we're looking at now, obviously that would be a preferred, maybe a preferred solution, even though what the neural net does for you is to reduce this huge space to some manageable space in which you can then do the Bayesian inference.
Yeah, what you're describing is, I mean, super logical in the sense that you have tons of parameters, like this 800 order parameters, right? And then if you try to do 800 parameter inference with MCMC or whatever, it's hopeless. But I'd like to see.
I don't know,
okay.
but okay. I mean, I suppose.
No, but there's, I mean, pure MCMC, kind of Metropolis Hastings. But there are newer, even MC methods, HMC, for example, and yeah, but true. Okay, but so my point was there are these high dimensional Bayesian methods. There's variational methods. I mean, yeah, that's something super similar to that in a completely different context. That's why I was asking about your integrations, about your moments and everything like that, and like what your data exactly constraints. But also, there's also purely neural methods in which you just infer. It's not MCMC anymore. It's like likelihood free stuff. But okay, I get what you are referring to for sure.
However, the main concern here is not the number of parameters. That is, if you take the neural network, usually we are weighted on 50 X point grids. So 50 times 8 is 400 parameters, or if we use 100 is 800 parameters. This is not that critical. Not even the number of data points, that is borderline because it's 5,000. 5,000 is not little, but it's already starting enough. Problem is that we don't have points in data space. In our function, the thing that we are trying to infer, we don't have a probe on that space. We have a very complicated mapping, and the very complicated mapping requires integrals, convolutions, and so on, and it starts being heavy. So at some point, point is that the likelihood is simple chi-square at the end. It's just a multi-Gaussian. But in order to compute the point to compare to data point, it's a very complicated function on of your functions that you're fitting. Yes.
Yes. Yeah.
Yeah. But the point is that the neural network doesn't care so much about how complicated is your loss function. for as long as you can model it.
Yeah, that's right. I mean, at the end of the day, I mean, you know, the function is very complicated in the sense that, say, a perturbative cross-section is something that contains polylogs. I mean, you know, obscure special functions, which are then integrated over and so on. But at the end of the day, we put everything in a grid. So at the end of the day, what the neural net sees is a bunch of matrices that are multiplied with each other and with a final vector. So it's
Indeed,
yeah.
as a function of the parameters, they are just a huge bunch of grids. That is a bunch of arrays, something like half a gigabyte or a few gigabytes actually of arrays. And then these few gigabytes of arrays, you have to fold. And if they were only linear functions, meaning a linear function from your parameter space, if it app itself to the object, it was quite simple. But then you have also quadratic, and you cannot do simple inference with Gaussians because at the end this is not entering. However, we have approximate solutions, exact solutions, so we want to implement the agency and so on. We believe to be feasible. Problem is just to qualify, so it's not clear.
So you see, Andrea, we managed to get close to your cutoff. We saturated it, I'm afraid.